Uh, I am Justin Swanhart. I'm a support engineer at Percona. I used to be a consultant and a trainer and a developer, so I've kind of done everything at Percona. And I'm going to talk to you about MySQL and InnoDB fundamentals. So we're going to talk about MyISAM and about InnoDB and some of the basic settings that you need to tweak in MySQL. So first off, MySQL is multi-threaded, right? Some other databases are multi-process. They spawn a new process when you connect, but MySQL is multi-threaded. So the main daemon is MySQL D. It runs in the background. It accepts TCP connections. It authenticates the users. It answers queries. And as I said, it's a one thread per connection model. So normally you have one thread for every connection. Now, there is a pool of threads plugin that's available now. This kind of puts a connection pool inside of the database. It's available in Percona Server and in MariaDB. It's not available in MySQL Community. You have to use MySQL Enterprise if you want to use upstream. But it is in both Percona Server and in MariaDB. It's pretty cool. If you've got tens of thousands of connections from lots of different servers, you can set up a small number of threads to execute concurrently, and it will balance your queries over those threads. So you normally put your MySQL settings in the my.cnf file. Normally lives in etc. If you're on Windows, it's my.ini. These config files, like I said, normally in etc. You can also put them in the data directory itself. So that's an alternate location if you want to do that. But it's usually best to put them in etc. If you're on various distributions, Debian, Ubuntu, they'll be in etc. MySQL, my.cnf. So there's two major sections that you need to worry about in this INI file or CNF file. The first is the MySQL D _safe section. Here you put things like open files limit, NUMA settings that you can set, various other settings that are related to the startup of MySQL. If you're using TokuDB, you can put a LD preload in there for the JE-malloc library. The MySQL D section has all the other settings. We're going to talk about various settings. One of them is, of course, your sort buffer size. But those go into the MySQL D section. So it's SQL 92. It doesn't have modern features like window functions or common table expressions or table functions. But it is SQL 92, so the majority of SQL is going to run against it fine. Unlike other databases, which are a monolithic storage system, MySQL has storage engines. So you can select a storage engine that's appropriate for your data storage needs. The two primary ones that I'm going to talk about are MyISAM and InnoDB. There's also TokuDB, which Percona just acquired, which is similar to InnoDB, but has a better compression and is right optimized. Indexes are B trees. MySQL doesn't have bitmap indexes or hash indexes. Everything is a B tree. And joins are nested loops, right? Indexed nested loops. There are no hash joins, no bitmap joins. If you don't have indexes for a join, it's going to do what's called block nested loop. So it fills a buffer up, it iterates over the table, comparing each one of the rows to each row in the buffer. Then it fills another buffer up and runs through the table again and again. So it's very similar to a traditional hash join. It does not perform well. So you want to make sure that you have indexes to support your joins. So transactions. MySQL is transactional, but it depends on which storage engine you use. If you're using MyISAM, you don't get transactions. But InnoDB and TokuDB are ACID compliant. I'll talk about that in a moment. And they also have XA, or distributed transactions. So if you have two systems that you need to coordinate in a transactional way, you can use XA transactions. The caveat there is that there are some limitations with XA transactions prior to MySQL 5.7. The new 5.7 that's coming out has much improved XA. InnoDB is the only storage engine that supports foreign keys. All the other storage engines do not provide the ability to use foreign keys. Now, traditionally, the advice has usually been don't use foreign keys. They add a lot of overhead. Unlike Oracle, they can't be deferred and they can't be batched. So every single row change has to do a lookup into the foreign index. So they can be really expensive. Also, there's no way to disable them on the fly. So if you have you want to do a bulk update, there's no way to disable the foreign keys. Now it is transactional, but it defaults to auto commit, right? So every statement that you run is going to automatically commit after that statement finishes by default. You can start new transactions with begin, start transaction, or start transaction with consistent snapshot. The difference between start transaction and begin and start transaction with consistent snapshot is that these two actually only begin the transaction once you touch a table. So if you start transaction and you don't actually hit a table for an hour, it's not going to hold a long-running transaction. But if you start transaction with consistent snapshot, it immediately starts the transaction in the transaction storage engines. Just a side note, there's also start transaction read-only. If you want to do a read-only transaction, it has less overhead than a read-write transaction. But select statements in auto-commit mode automatically use a read-only transaction, so it's not really something that you need to worry about. So commit writes changes into the database, and I'll tell you exactly what happens at commit a little bit later. Rollback undoes or rolls back the changes. So if you accidentally delete a bunch of rows, you can type rollback, and those rows will not be deleted. And you can use save points. So a save point allows you to set checkpoints along the way. You may have checkpoint A, checkpoint B, checkpoint C, and you can roll back to any one of those checkpoints with a rollback to save point command. So acid, right? You don't want to drop acid. Well, I mean, I guess that depends on your recreational level of drug use, but so it's atomicity. Atomicity means that all the changes in a transaction happen or none of the changes happen, right? You can't have a half-updated table if a transaction fails. So that's atomic. Consistency means that when I do a read and I do that same read again, even if it's an hour later, if it's in the same transaction, I'm going to see the data as it was an hour ago. Isolation means that I can make changes and those changes aren't visible to other people and their changes aren't visible to me. And durability means that once I commit, it's guaranteed to be available and committed in the database. There's no way to lose that data that has been committed. So durability is very, very important. Now, what's the opposite of acid? Base, right? So basically available service, and that's eventual consistency, right? So this uses what's called the Aries protocol for consistency. So MyISAM has been around forever. It replaced ISAM in version 3.2.3. I believe it was 3.2.3. It stores data internally in a heap. It's just a row back-to-back storage, very simple format. ISAM is index sequential access method. So this was invented a very long time ago. It can use either fixed or dynamic rows. If you use fixed rows, the rows are fixed width, but you can seek through the file a lot faster because you don't have to worry about the dynamically sized rows versus the dynamic row format. The indexes in MyISAM point to actual file offsets in the data file, right? These aren't like InnoDB indexes, which we'll talk about, that are index organized. So they're physical offsets. And it has table level locking. So if you're inserting into a table or you're updating a table, no one else can update that table or even read from that table while the update is happening, right? So it's not good if you have high concurrency. If you have low concurrency and mostly reads, it can be okay. But it has a lot of other problems too, which I'm going to talk about. So MyISAM caches indexes in what's called the key buffer. So it's configured with key buffer size. That's pretty intuitive. That controls how large it is. You can set key buffer size on the fly as well, so you can increase it or decrease it, unlike the InnoDB buffer pool. The indexes for MyISAM are stored in the MYI file. So we have an FRM file. All tables have an FRM file. And MyISAM tables have an MYD file, which contains the data, and an MYI file, which contains the indexes. There's not much sense making the key buffer larger than the sum of the MYI file sizes, right? Those are the size of your indexes. So you can look at the MYI files. If they take 2 gigs, well, it makes no sense to have a 4 gig key buffer because you only have 2 gigs of indexes. You can create more than one key buffer as well. So if you have a bunch of different tables and you want them to have different key buffers so that the data for each of those tables stays in one particular key buffer, you can do that. There's also another setting, it's not on the slide, but it's called key cache division limit. It sets the midpoint insertion strategy for the key buffer. So you can tell it to insert it, say, 30%, and that will prevent churn in the key buffer. MyISAM does not cache data. It relies on the OS file cache to cache data. It only caches indexes in the key buffer. So you have to make sure you have enough free memory available to take advantage of that OS cache. It also uses it to cache writes. This is why MyISAM, when it crashes, it gets corrupted because those writes are written out into the OS file cache and they're never synced to disk. It lets the OS sync them in the background. So don't set the key buffer too large because you need to have an available OS cache. MyISAM is not transactional. It's not even atomic. You can't roll back. So pressing Control-C in the middle of an update is going to leave some rows updated and others not. This can also cause a big problem with replication because it'll say it updated 10 rows on the master and then it runs on the slave and it updates 1,000,000 rows. And it goes, oh, there's a different number of rows modified on the master and the slave. And now the master's out of sync with the slave because the slave wrote a bunch of changes that the master never wrote. And like I said, because it uses the OS buffer for writes, server crash can leave your tables in an inconsistent state. And then you're going to have to repair your tables. But let me just show you real quick the... you can't read it. Anyway, if you hit Control-C in the middle of MyISAM update, it'll just update half the rows or some portion of the rows, and the rest of them won't update. So. Okay. Well, this has been fun. So if the server crashes and there are pending MyISAM writes, you're going to have to repair your table. You can use the repair table command. There's a command line tool called MySQL check, which can automatically check your tables and see if they need to be repaired. And if your server is offline, you can use the MyISAM check utility. And it can be really beneficial to use MyISAM check offline because you can force it to do repairs by sort rather than repairing by the key buffer, and it can be orders of magnitude faster for large tables. So keep that in mind. You might want to use the MyISAM check utility. But you have to use that with the server shut down. You can't have the server running and run MyISAM check. This repair is basically, it's like an FS check, right? An FS check on a non-logging file system. So it's going to have to read the entire data file and rebuild any of the broken indexes. And it can take a very long time. A very long time. So MyISAM is best for non-critical data, right? You can have a slave that's MyISAM, and you have a source of truth that's your InnoDB master, and you're doing reporting or whatever on this MyISAM slave, and if it crashes, you can just rebuild it from the master. MyISAM does not have checksums, right? So if you have a 1-bit error in your file, a 1 could turn into a 2 billion, right? So you have to keep that in mind. InnoDB has checksums. And lack of concurrency means that MyISAM really is only good for read-mostly workloads. It's really not good for read-write or write-heavy workloads. Now, InnoDB, in contrast, is 100% ACID compliant, right? So it has a log file, And the log is written to as you make changes in the database. And if the server crashes, it can use this log to recover. So it does what's called roll forward and roll back recovery. So in the log, every transaction has a transaction begin marker, and every transaction should have a transaction end marker. So when the database comes back up after a crash, it rolls forward all of the changes, even changes that were uncommitted, and then it finds any transactions that don't have end markers, and it rolls those transactions back. So it's two-phase. Now, the problem here is this log file is f-synced at every commit. So if you're doing 200 commits a second, that's 200 f-syncs a second. That's as much as a regular rotational disk can handle, right? So you're really limited to about 200 transactions per second unless you have a battery-backed RAID controller or flash, right? Now, you can relax this. You can set InnoDB flush log at tricks commit to 0 or 2. If you set it to 2, every commit flushes the data to the OS cache, but not all the way to disk. If you set it to 0, there's no flush. Regardless, every 1 second, this file is f-synced. So basically, if you relax the durability here, you lose up to 1 second's worth of transactions when the server crashes. For most people, this is acceptable because it's just like you crashed 1 second earlier, right? So it's not that big of a deal. But if you are at a financial institution and you can't lose any transactions, then you have to make sure that you're in InnoDB flush log at tricks commit equals 1, which is the default. So unlike MyISAM, InnoDB caches both indexes and data, right? We call this the buffer pool. It's similar to the SGA in Oracle, right? So you configure it with InnoDB buffer pool size. Now this defaults to a very low value, only 128 megs, so you have to make sure that you tweak this value or you're not going to get good performance from InnoDB. One company had me come all the way to Florida to help tune their system, and all I had to do was increase that from 128 megs to 2 gigs, and all of their problems went away. So the general rule here is 80% of RAM, right? But obviously, if you've got the 100 gigs of RAM or 512 gigs of RAM, like a lot of systems do today, you're going to want to make that larger. You don't want to be wasting tens of gigs. No reason to do that. So your mileage may vary depending on how big you need that. If you're using multiple storage engines, you have to split this over the different storage engines. So if you give 4 gigs to MyISAM and you have 16 gigs of RAM, you can't give the tremendous amount of RAM to InnoDB. Same with TokuDB. If you want to mix TokuDB and InnoDB, you need to make sure that the buffers for the various storage engines don't use all of your available RAM. So the buffer pool itself is a least recently used list. So it's a linked list of pages. When you access a page, it goes to the top of the list, and then it gets moved down the list. And if it's accessed again, it moves back to the top of the list again. There's a midpoint insertion strategy. It's InnoDB old pages per InnoDB old blocks PCT. It defaults to 30%. So the pages end up at the kind of near the end of the buffer pool, and then they'll get moved up if they're accessed again. The reason for this is so a table scan that runs doesn't push all of your good pages out of the buffer pool, which has traditionally been a big problem with these type of LRU. There's also the adaptive hash index. The adaptive hash index is maintained automatically in the background. You don't have to configure it. There's nothing to configure it with, actually. But InnoDB is aware of hot pages or hot parts of tables and automatically builds a hash index for the portions of those tables. Now, this is for secondary key lookups, because the secondary key lookup in InnoDB is more expensive than a lookup in MyISAM. In MyISAM, you read the index file, you do a seek directly to the file position, and you're done, because MyISAM has the file position. With InnoDB, the tables are index organized. They're clustered tables, right? So the data for the table is actually stored along with the primary key entry. And so very, very different from MyISAM. The secondary indexes, they all have a copy of the primary key, right? Because they have to actually access the table and primary key to get the data out, right? So rather than have one O log n operation, now you have two O log n operations, where n is the depth of the B tree. So you should keep your primary key very short. Ideally, it's going to be an auto increment. It should definitely not be a UUID, ever. You can't insert those in sorted order, right? And they're long, and they're text, right? We want a nice short integer primary key that we can insert in sorted order as much as possible. This one's kind of a bummer. InnoDB uses more space than MyISAM. It usually uses at least twice the space of MyISAM, and it's because all of the rows have to have a transaction ID in the row. And this is so it can get a consistent view over time. Like I said, when you come back and you run a select an hour into your transaction, you have to see the data at the same state it was that hour ago. Well, every row has a transaction ID in it, and the database knows, I'm transaction 30, so I can't see anything greater than 30. But it requires extra space for that. There's also a rollback pointer. So the rollback pointer points into undo segments, which we'll talk about in a few moments, but that also takes up extra space. And pages have a 1516 fill factor. So all the pages have a small amount of space reserved so that you don't have to split the page if you update a value and you make it larger. Now, selects for InnoDB, they don't normally take locks. You don't get any locks for select statements, even in read committed, or repeatable read. No locks. So not like DB2 or Microsoft SQL Server, except unless you use for update or lock and share mode. In those cases, those obviously you're asking it to take locks. So it has row level locking, fine grain locking, right? It can have table level locks if you need to lock a table, but they're not used by default. You got to be careful, because a range scan is going to lock all of the rows that it touches. So, and if you don't have a good index and you update a table, you could end up scanning the primary key and locking almost all of the rows or all of the rows in your table. So you need to make sure that your tables are indexed for your update statements. I have little asterisks there because if you're in read committed, rather than repeatable read, which is the default, if you're in read committed, the locks that don't, the rows that don't match the scan are actually released. But that's only if you're in read committed, and most people are in repeatable read. The locks are held for the duration of your transaction, right? Not for the duration of the statement. So if you update a row at 5 a.m. and you don't commit that transaction until 10 p.m., that row is going to remain locked that entire day. So rollback and undo, they're the same thing. InnoDB has rollback segments. In the past, there was only one rollback segment, but now it comes by with 128 by default, which should probably be more than enough for anybody. It's like 150,000 concurrent transactions or something. Every transaction gets a slot in one of these segments. The rollback segments can't be cleaned up past the oldest running transaction. This is extremely important because the more history you get, the more data the database has to look through, and the slower and slower things get. So you should make sure you have short-running transactions. When I first started at Percona a long time ago, I ran into a pathological case of this. A monitoring company in Germany, they had a 2-week running transaction. And doubly worse, they decided to purge 6 months of historical data during this period. So their rollback segments grew to 175 gigs. And they never shrink. So this is not good. They're stored in the central table space unless you configure external undo segments in 5.6. And you can't do that after you've created your database. So most people have these rollback segments in the central table space, and once it grows, it can't shrink. So you don't want that to happen. Also, your indexes get bloated if you have these long-running transactions because the indexes have to have multiple copies of data to be transactionally consistent. You can do an index-only scan in MySQL, which means that the index itself has to have enough transactional information and multiple views of the data to provide a consistent view for those index-only scans. Later on, the purge process comes along, and it cleans up the rollback segments, it cleans up deleted rows, and it cleans up these extra entries in your indexes. But cleaning them up leaves holes. So every once in a while, you should use the optimize table command in order to get rid of these holes in your indexes.
If your table is pretty big, if you optimize the table, it's going to alter the table, right? It's going to allow the table for a long time.
Yeah, yeah.
So you should clean up the table, make the table relatively smaller before you optimize.
You should, yeah, you should try to do that, yeah. There's rumors that 5.7 will have online optimize, but I haven't tested it. So yeah, like I said, the InnoDB buffer pool size is the most important parameter that you have to worry about. That's your cache for your data. That's your LRU. If you have the buffer pool size set too small, you're not going to get good performance. There's also InnoDB log file size. So this controls the size of InnoDB's write-ahead or transaction log. Now, normally, there are two of these log files. There's IB log file 1 and IB log file 2. If you want, you can change the InnoDB log files in group parameter, so you have 3 log files, but there's really no reason to do it. They're just one big circular buffer, so just keep 2 log files. Divide your desired size by 2, right? So if you want 10 gigs of logs, set this to 5 gigs. The log buffer size defaults to 8 megs. Unless you're doing a lot of concurrent transactions, like hundreds of concurrent transactions, or you're writing big blobs, you probably don't need to modify this. But this is the maximum chunk of data that can be written into the log at once. So if you have to write a 64 meg blob, it's going to have to take 8 passes over this buffer to get the data into the log. And InnoDB file per table, it's the default in 5.6, but not in 5.5. This puts every InnoDB table into its own file on disk rather than using one big shared table space. The biggest advantage here is that if you truncate or drop that table, space gets reclaimed on disk. If you use the central table space, it's not going to be able to reclaim that space. The central table space can't shrink. So it makes a lot of sense to use InnoDB file per table unless you have hundreds of thousands of tables. In that case, startup time can be affected because all of these tables have to be opened and checked, and the file handles used by the operating system are going to go up a lot. It causes problems with extra backup because extra backup has to keep copies of the files open. So yeah, if you have hundreds of thousands of tables, you probably want to use the central table space.
The log file, IB log file, MySQL does not save such, so it is only used during the crash after the
Right. Yeah, it's not used during normal operations. Yeah. So other important settings, the sort buffer size. It's important to not set this too big. I know that sounds counterintuitive, but you want the sort buffer to be able to fit in the CPU cache. So you probably don't want it to be more than 2 megs. And I've done lots of various testing. It really does not get any better after 2 megs. It actually will start to fall off fairly rapidly. Facebook tends to use 32K for their sort buffer size. Right? So it's unless you're sorting huge amounts of data, you really don't need to worry about changing it. The default is 256K. Query cache size should always be 0. The query cache is evil. It has a single mutex that's held for every single query. And if your queries return large amounts of data, every 16K of data has to release and reacquire that mutex again. So very, very expensive. And it becomes fragmented very easily. And use memcache or Redis or some external cache that you have more control over. Or I like to put stuff into a materialized views, have a materialized view toolkit. Lots of other options rather than using the query cache. Table open cache. Table open cache is mostly for MyISAM. You don't want to set table open cache too large because it's linearly searched. It does not have a hash-backed structure. So the larger it is, the longer it takes to open tables. So there's kind of a trade-off between keeping things in the cache and then making the cache too large. So I usually don't set it above around 2K, 2,000 or so. Table definition cache, on the other hand, it is hash-backed, and it can be set large. And it's very, very important, there should be underscores there, sorry. Very important that you set the table definition cache large enough because InnoDB now in 5.6, the amount of data that's stored in the in-memory data dictionary is controlled by table definition cache. In 5.5 and earlier, the in-memory data dictionary can grow unbounded. So if you have hundreds of thousands of tables again, you could waste gigs of RAM on the data dictionary in RAM. But this prevents that from happening. So I usually set this to 16,384. Of course, the slow query log, log slow queries, and slow query log file. These are how you can find out information about the queries that are running and what's running slow. So a lot of people will set long query time, which isn't listed here, but long query time to 0, which will collect all queries into the slow query log. And then you can use a tool like ptQuery Digest to examine that log and print out the most frequently run queries as well as the most expensive queries. Because you may have a 1 millisecond query that you're running 1,000 times a second when you could cache that query and get rid of all those round trips. So it's not just slow queries you're worried about. You should also worry about frequently run queries. And that's it. You should use an external cache. Use a memcache or Redis. You store it in the table, right? Yeah. If you read mostly, the query cache can be okay. The biggest problem with the query cache is that if you change a single row in a table, every query that uses that table has to be invalidated in the query cache. And that's a linear scan through the query cache. So if you set the query cache to, say, a gig, every single row change has to scan through a gig of RAM, which obviously is not going to perform very well. And so, I mean, that's what I would call coarse invalidation. Whereas if you use an external cache, you can control the invalidation for yourself.
Is like query cache is still enabled by default?
No, it defaults to be off now.
It's off now, okay.
Yeah.
Because earlier versions had on.
Yeah.
So it was very common for people to test against one query and say, wow, this is very fast, this is very fast. But then they were not really testing in real life.
Yeah. I mean, another thing here, I mean, I had a customer who had a data warehouse, and they would run queries all day long, and all their queries would end up in the query cache, and then their system would completely fall over as soon as they did any ETL in the evening. They wouldn't be able to process any queries anymore. And they moved to an external cache. They used memcache, and that eliminated that problem for them.
Query cache means we are talking about storing the result set, or we are just talking about the storing the statement?
It stores the result set.
Okay.
Yeah. No. No, it's all or nothing.
Query cache is like something which is theoretically looks very good when you read through the manual, but in practically almost nobody uses it.
Exactly.
One out of 100 customers use it.
Yeah.
Nobody.
It's that mutex being held for every statement is killer, and then the fact that you have to invalidate all the queries against the table anytime it changes, it really makes it very ineffective.
That can be all the way.
Yeah.
Did you say that space deleted is not reclaimed in the center table space?
Right. So if you delete a million rows, that space is not reclaimed on disk. You can reuse it for new insertions, but it won't be returned to the OS.
So the rollback segments stay in the center table space.
Right. In 5.6, you can use external rollback segments, but if once they grow, they can't shrink again. You have to wait till 5.7 for that.
I guess that's why people are using files per table, like most like shops.
Yeah.
Files per
Yeah. Yeah. I mean, unless you have lots and lots and lots of tables, it makes sense to use file per table. That's why it defaults.
Still use file per table.
Yeah.
It's the optimized table of health.
It defragments the table. It gets rid of all the holes in the indexes. But if it's in the central table space, it won't free up any space to the OS. No, the central table space never shrinks. Right, because when you optimize the table, it'll write it out as a new file, so you'll temporarily use twice the space, and then the old file is removed.
One question on the MyISAM key buffer size,
Mhm.
and then you talked about the InnoDB buffer size.
Mhm.
So MyISAM just holds the indices,
Right.
and the InnoDB one holds the index and the row data.
Yeah, everything in InnoDB is an index. The table is a primary key, or and that's your table, so it's an index, and the indexes are obviously indexes. So it really only caches indexes, but that's indexes and data because of that.
So does that mean when you do a read of MyISAM, that it always has to go to this to get the row data?
Unless it's in the OS's file cache. That's why you want to make sure you have enough RAM available to the OS can use the file cache.
But you can't really control that.
No, there's.
You don't know what's
No, there is there's a command whose name is escaping me at the moment that will allow you to see what portion of a file is in core, but I don't remember what the command is. Well, thank you.